Welcome to our presentation. This is a talk about stronger targeted poisoning attacks against malware detection. My name is Shintaro Narisada. This is a joint work with Shoichiro Sasaki, Seira Hidano, Toshihiro Uchibayashi, Takuo Suganuma, Masahiro Hiji, and Shinsaku Kiyomoto. Recently, the security risk against attacks on machine learning systems is a major threat. Data poisoning attack proposed by Nelson et al. Is one of the indiscriminate attacks against machine learning systems. In this attack, we assume that an attacker can access the training data and he injects poisoning data to the training data before training process. The attacker's purpose is to degrade the entire accuracy of the targeted model by injecting a small amount of poisoning data to the training data. The poisoned model is trained on the union of the sets and the model misclassifies the input. The algorithm is relatively simple because we only need to consider maximizing the entire loss of the model. However, the attack situation is unrealistic since the existence of the attack is easily detected by observing the entire loss of the model. A more realistic variant of the poisoning attacks is targeted data poisoning attacks proposed by Munoz et al. In the attack, an attacker aims to degrade the accuracy of only a specific class. In this figure, the poisoning data are injected to degrade the model to misclassify only samples in the red class. This attack is rather realistic since it can reduce the accuracy of only a specific class while keeping almost the same entire accuracy. But it is more difficult than the normal poisoning attacks to succeed in the case of multi-label problems. Sasaki et al. Extended the attack and they have applied it to the malware detection problem. The malware detection is a binary classification problem to classify the input as benign or malicious. Malware is grouped and labeled by its family name. The attacker's purpose is to misclassify only targeted malware family as benign and not misclassify the others. In their experiment, they achieved 85% attack success rate by adding 15% poisoning data. On the other hand, they assumed that a defender did not take any defensive measure. In our paper, we consider common defensive methods called data sanitization defenses against targeted data poisoning attacks. And we propose stronger defense-aware algorithms that evade the data sanitization defenses. Our algorithm is an online learning algorithm which combines the label flip attacks proposed by Shao et al. And an idea from the optimal loss analysis proposed by Steinhardt et al. In our experiment, our proposed algorithm achieved highest attack success rate for two malware datasets. Moreover, as for the poisoning data generation, we implemented an optimization solver in our algorithm, and our algorithms achieved 1000 times faster than previous algorithms. First, let me explain the Munoz targeted data poisoning algorithm. They formulated the targeted data poisoning attacks by considering an optimization problem regarding poisoning data. A poisoning point X is generated by solving the following bi-level optimization problem. First, the optimized model W hat is constructed by minimizing the loss over the training data DTR and a positioning point X and its label Y bar target, in which bar means label flipping and Y bar target is 0 or P9 for malware classification. Then, the positioning point X is generated so that the loss of the minimized model W hat over the attacker's validation data D-bar bar is minimized. D-bar bar consists only of target data from the original validation data, with their labels flipped. This optimization formula was embodied as a gradient-based learning algorithm. In the algorithm, an initial positioning point x0 is chosen randomly from targeted malware in the training data. Its label Y bar target is flipped from malware to benign. Then, the loss minimization problem is solved alternately by gradient descent algorithm until the positioning point is converged. The model double hat is constructed by minimizing the loss over the training data DTR and the current positioning point xi. The negative gradient of xi of the attacker's validation data D-bar bar is computed and xi is updated. Finally, single positioning point xi is generated. Sasaki extended the Munoz method by considering the constraint term with regard to L2 norm. Beta is a hyperparameter for the constraint term with a value greater than or equal to 0. If beta is large, then positioning point X is generated in the vicinity of the randomly selected goodware X good. Sasaki's algorithm can evade the outlier detection if beta is large, since the positioning point X is located in about the same place as the goodware. But the attack success rate is reduced. So we note that both Munoz and Sasaki methods do not consider a defender applies a data sanitization. We would like to apply the data sanitization defense against targeted positioning attacks. In general, data sanitization defense considers a feasible set F and removes points outside of F. So the model W trains points in DTR and DP on F. A well-known techniques of the defense are the sphere defense and the slab defense. The sphere defense uses the L2 distance between the positioning point X and the centroid μy, and removes points where the distance is larger than Ry. The slab defense uses the absolute value of the inner product of X minus μy and μy bar, and removes points where the distance is larger than Sy. In the following, we use the sphere defense as a data sanitization for simplicity. First, we present a basic defense-aware targeted poisoning algorithm. We assume that a defender uses logistic regression model for the malware detector, as well as Sasaki. The idea is simple. The initial positioning point x0 is chosen from the targeted malware located on F-good, and the label is flipped to goodware. The point xi is updated by the gradient descent using Munoz method so that it does not go out of F-good. If xi is outside of F-good after updating, xi is projected to the closest position of F-good by adding the perturbation delta. Delta is the shortest vector to the F-good sphere. The problem with this algorithm is high computational cost of poison generation, because basic algorithm needs to compute the minimization problem about the model W for each xi. Basic algorithm must solve the loss minimization of W many times to generate a single pausing point due to the order of the optimization. Basic algorithm generates many models redundantly by computing argument W to create one pausing point X. So, our goal is to reconstruct the optimization problem that requires only one model creation. To achieve it, we consider to swap the order of solving X and W to reduce the computational cost. To do so, we firstly include the term about the loss other than targeted malware in the optimization formula. We define a superset outlined DP such that adding any element of outlined DP to the training data does not affect the loss DTRN by considering that the loss of W hat DTRN is almost equal to the loss of WC DTRN, where DTRN is a dataset consisting of non-targeted malware and goodware, and WC is a clean model trained on the original dataset. We assume that any DP are chosen from outlined DP. Intuitively, it is natural to introduce outlined DP into the equation of the targeted poisoning attacks, because in targeted poisoning attacks, the entire accuracy except for the targeted malware can be kept as high as the accuracy for the unpoisoned model. We will explain how to choose the poisoning data in outlined DP later. If we assume that DP is chosen from outlined DP, then the optimization problem is approximated by the formula. We will leave out the details of the variation of the formula, but you can see that the order of solving X and W are swapped. Not only that, minimizing the loss of DP is replaced by maximizing the loss by considering label complement. The remaining problem is how to generate DP in outlined DP. Our strategy is to plot the poisoning point close to the targeted malware, to only increase the loss for the targeted malware. A basic strategy is to apply a variant of label flip attacks proposed by Shao et al. In this attack, an attacker creates poison by flipping the label Y and overlap the point on the targeted malware. To include the intent of the loss maximization into the label flip attacks, we also consider the loss maximization within a small ball. Here, a small noise D is added to X so that the loss of X plus D is maximized. Finally, we constructed an online learning algorithm that combines our ideas. Unlike the method of Munoz, a pausing point is generated for each loop by maximizing the loss within a small radius R. Moreover, the maximization problem for X is fast solvable if we use an optimization solver, since we use logistic regression as a model. If R equals to 0, the algorithm generates poisoning point by the label flip attack. On the other hand, the model W is run in the entire loop. At the end, full pausing data DP is generated. We experimented the performance of 5 algorithms, Munoz and Sasaki algorithms, and our basic algorithm, label flip algorithm, and the streamlined algorithm using an optimization solver. We used 2 types of malware dataset. Ransomware dataset consisting of binary variables and Microsoft malware dataset consisting of continuous variables. We choose one malware family as the target and the remaining 8 as non-targeted malware. First, we evaluated the defensive performance of the sphere defense. The table shows the poison removal rate for adding 36 poisoning data. As you can see, the sphere defense removed most of poisoning data for Munoz algorithm. On the other hand, the sphere defense failed to remove poisoning point for Sasaki and our algorithms. This is because these algorithms generate poison so that they are inside the sphere if good. Next, we compared the attack success rate, varying the poisoning rate from 0% to 15%. The red lines correspond to the attack success rate. Green lines correspond to the false positive rate of the goodware, and blue lines show the false negative rate of the non-targeted malware. We omitted Munoz algorithm since almost poisoning points were removed. As a result, there was no significant variation between algorithms for binary dataset. The reason is that our algorithms failed to move the vector to the desired coordinate since the perturbation is rounded to 0 or 1. For continuous dataset, Basic and Solver achieved the highest attack success rate. For non-targeted malware, the classification accuracy is slightly reduced by adding poison data. We confirmed that the classification accuracy for the benign software is not affected. We also compared the computational costs of each algorithm to generate 36 poisoning points. As you can see, our proposed online algorithms are about 1,000 times faster than the gradient-based algorithms. In conclusion, we propose two targeted poisoning algorithms, the basic variant and the streamlined online learning algorithm that evades the data sanitization defense. Our streamlined algorithm is based on the combination of two techniques, label flip attacks and optimal attack strategy to maximize the training loss. Our algorithm achieved an attack success rate of 19% by adding 15 poisoning data. Our algorithms are about 1,000 times faster than previous algorithms. Thank you very much for your attention.